Shap-E is a novel model designed to generate 3D assets by directly producing implicit functions. Unlike traditional approaches that output specific representations, Shap-E generates parameters for functions that can be rendered as both neural radiance fields and signed distance functions. This dual capability enables Shap-E to efficiently generate textured meshes and detailed 3D scenes. In the image, we see examples of the diverse assets Shap-E can produce. Creating 3D models is far more complex than generating 2D images because it requires accurate representations from multiple angles. While models like Point-E rely on generating point clouds that need explicit rendering, Shap-E simplifies the process by generating parameters of implicit functions directly. This allows for more flexible outputs and quicker convergence times. The comparison in the image illustrates the difference in output quality between Point-E and Shap-E. An implicit neural representation, or INR for short, maps 3D coordinates to features like color or density. These INRs are flexible and can be queried at any resolution, which makes them perfect for representing 3D assets. Shap-E uses two key types of INRs. Neural radiance fields, or NeurIPS for short, represents 3D scenes by mapping coordinates and viewing directions to RGB colors and densities, allowing rendering from any viewpoint. Signed distance functions, or SDFs for short, are functions that define a 3D object by mapping each point in space to its distance from the object's surface. A specific type of SDF is called a DMT-ET, which is used in Shap-E for efficiently generating 3D meshes with texture. To train Shap-E, the model relies on a vast dataset of millions of 3D assets paired with text captions and point clouds. For each object, 60 different views were rendered to capture all angles, ensuring more detailed outputs. Shap-E's 3D encoder plays a crucial role here. It processes both point clouds and multiple views of the 3D asset, then outputs parameters for a neural network that represents the 3D shape. The encoder feeds this data into a diffusion model for further refinement. Shap-E uses latent diffusion models to refine and generate its 3D assets. Diffusion models gradually denoise a random input to reveal a structured output, in this case, a 3D model. Latent diffusion focuses on generating samples in a compressed, lower-dimensional latent space, making it more efficient than pixel-level diffusion. In Shap-E, the model predicts the parameters of implicit functions rather than explicit representations like point clouds. This method allows Shap-E to efficiently generate NeurIPS and SDFs from text or image prompts. Classifier-free guidance is used to improve the clarity of outputs by adjusting the model's predictions during sampling. Shap-E's training happens in two stages. First, the encoder is trained to generate parameters of implicit functions from 3D assets, mapping them into a latent space. Then, a conditional diffusion model is trained to predict these latent representations, conditioned on either text or images. This two-stage process allows Shap-E to generate complex, multi-representation 3D assets in just seconds. As seen in the diagram, text or image prompts are transformed into detailed 3D outputs using this approach. Once trained, Shap-E can generate both NeurIPS and SDFs. NeurIPS are rendered by tracing rays through 3D space, using the NeurIPS function to sample color and density along each ray. This allows for realistic scene rendering from any angle. SDFs provide an implicit representation of an object's surface, allowing Shap-E to create detailed, textured 3D meshes. These meshes can then be rendered with high-quality textures using techniques like marching cubes to extract the surface. One of the biggest advantages of Shap-E is its speed. It can generate high-quality 3D models in about 13 seconds using a single V100 GPU. This makes Shap-E much faster than optimization-heavy approaches like Dream Fusion, which requires significantly more time to produce similar outputs, albeit in high quality. As shown in the chart, Shap-E strikes a great balance between speed and sample quality, outperforming many other models. Although Shap-E excels in generating 3D assets, it does face some limitations. For example, it can struggle with creating highly detailed scenes or multiple objects interacting within the same space. Also, fine textures can sometimes lack sharpness. Here is an example where Shap-E struggles to generate precise details. Shap-E is a significant advancement in the field of 3D asset generation. By using implicit functions, and latent diffusion, it produces 3D models quickly and efficiently. Shap-E's potential applications span across gaming, virtual reality, augmented reality, and even 3D printing, where the ability to generate custom 3D objects from text descriptions offers immense possibilities. Thank you for watching this presentation on Shap-E.